This one, just that one.
Yeah.
So, you know the purpose of the timing was that kind of I charge like that you can see here, but we make what cheese, mac and cheese. I charge.
It's a tax.
Yeah.
It's a French tax.
Right. But there's like the gold bucket, silver bucket, gold bucket, eBay.
You peasant.
Wow, that's it's not like it's the part of that's what that's true.
Another stuff?
No,
Definitely.
it's like a funny triangle. One of those Facebook type videos.
I don't know what you're talking about. Honestly.
It's like how many squares do you see in this picture? If you like say 4, well, that means you're this or that. And like, yeah, you have like grown-ass adults fighting over how many squares are in this picture. It's so humorous.
Well, yeah, I mean, you'll have to like email me the link to that and I can get in on the fight. But yeah, I don't know. No, that's not what this is at all. This is the Sierpinski triangle, which is a fractal nature, which means that I'll tell you what a fractal means. If I take this guy, yeah, let me take this guy. Yeah, okay. Now, if I take it and if I shrink it, right, and I can like overlay this. Well, if I shrink it just right, I can overlay it on top of, I've done a little too long there. On top of the previous one, I'll get exactly what I had. So there's a scaling invariance. You take something, you scale it down, it looks exactly like it was before, and you can kind of move it around, right, to other parts of it. Right? So this is actually what a fractal does. It has this kind of weird scale invariant. And there's actually a lot of interesting natural things, natural structures that have a fractal nature to them. But we're going to see this come up in kind of a silly, funny way in a second, out of the blue. Actually, right now. Well, not right now, in a second. As a part of reviewing something that I know you guys all learned in high school, or middle school, or elementary school. I don't know what you guys did, but you did something. And we'll see this thing come up in a surprising way, I think. All right, so what do we want to, what I want to do today is I want to remember we're talking about these Hamilton paths and circuits, right? And where I left off was I started talking about the complete graph and considering counting like the number of Hamilton paths, say, on the complete graph. So let's recall what a complete graph is. The complete graph Okay, n. So here n. Well, you guys tell me, what is n again? If I write this notation, what is n telling us? Yeah, the number of vertices. This equals the number of vertices. Good job. Oh, you guys are great. Don't get used to it. Come on. All right, so is the number of vertices. And so last time I said the number of Hamilton paths equal to n factorial. I say that? I don't know if I said that or not. I didn't say that. Okay, so then let me say it now. Last time. What is, does everyone, okay, how many of you remember notation like this? Wow. You've never seen this? That surprises me. Not
I've never seen an exclamation point.
really.
I don't think that was in college.
I'm seeing my enunciation has exclamation points all over it.
Just not excited about math.
You're not excited. Yeah, this is not last time the number of Hamiltonian paths was n factorial. I haven't said the n factorial. See, this is not wow. This is, okay. This does not equal wow. Okay. All right, so this is not what it is at all. This is n. Okay, good. So good place to start. And this is reads n factorial. It's a very simple thing. So it may look surprising, but very simple thing. What it means, so n should be a whole number, I guess, if we call them, right? N should be, or I don't know, natural number, I guess. It should be something greater than or equal, well, 0 or 0, 1, 2, and so on, a counting number. Anyway, and then n factorial is going to equal, you take n and you multiply it by 1 less than n. Multiply that by 2 less than n until you get all the way down to 1. Also, we have a convention, 0 factorial. This is just going to equal 1. That's convention. That's the notion of n factorial. That's what it is. So let's look at some numbers. So, okay, so as I just said, 0 factorial is 1. 1 factorial is equal to 1, you know. 2 factorial equals 2 times 1. 2. 3 factorial, 3 times 2 times 1, that's 6. Factorial. Now this is really, this is, you guys, is it starting to come back? A little bit. How many is in the triangle?
Like, you know, like when you stack cups and then you have like something on the bottom.
I know how to stack cups. Talking about beer pong? What are we talking about here? I know what you're talking about. Huh?
Find out like how many different like scenarios there are.
Guys, you're right. You're all right. You're right. You're right. There's all sorts of things. This is like a magical world that's opening up to you now. That should have happened when you're in elementary school for sure, or middle school. But this is a like factorial, and as we'll see in a second, what I'm going to talk about with this triangle, this gives you answers to all these types of questions. I mean, there's all types of counting questions, probabilistic questions, statistical questions. A ton of these can be answered using this notation and this idea. So there's a lot here for sure, a lot of answers to a lot of different questions. So you guys are all right. You're absolutely right. I know what you're right about, but you're right about something. I leave you. Okay. Okay, 5 factorial. 5, 4, 3, 2, 1. It'd be 120. Now, the reason I want, okay, so I can't, I don't know. I guess like we can keep on going 720, so on and so forth. But the thing I wanted to illustrate here is that this starts getting bigger. Right? It starts getting bigger pretty fast. You guys, I asked you this before, but I asked you this before. You guys have all seen exponential growth and or heard about it, right? And everybody said yes, right? Factorial is faster than exponential growth. It's like super exponential. It's really fast, grows very rapidly. In fact, there's a way of taking this function and sort of extending it to real numbers called the gamma function. I won't talk about that. But it's an important function for statistics and math. Anyway, let's get to these questions and these observations that you guys are talking about. What does this thing give us? Well, it gives us a lot. It gives us a lot. But what is the main thing? If you think of n factorial, what is n factorial counting? Well, one thing we said is it's counting the number of Hamilton paths on a complete graph. I want to say that we have 3 kind of interesting notions. The number of Hamilton paths, on Kn. We have n factorial, this thing we just learned about. And we have something I did mention last time. And people said, oh, I remember that. Or at least one person kind of said that. Permutations. And I'll say of n symbols. They could be, the symbols could be letters or shapes or whatever. These are, I should say, number of permutations. These are all equal. All the same number. And factorial. Let's see this correspondence illustrated in a particular example. So let's just start with something kind of small, n equaling 3. Let me draw my graph, K3. It's just a triangle here, right? And I'll label the vertices A, B, C. Now, we can do, let me make 6 of these guys by the magic of iPad. I can look at 6 of these fellas and we can, so 6 is certainly 3 factorial, right? We just calculated that. It's 3 times 2 times 1 equals 6. So I just drew 6 triangles. And for each of these triangles, I can write a path. So I'll go A, B, B, C. I can go A, C. Let me direct it. A, C, D, B. I can go B, A, A, C. I go BC, CA. Or I can start at C and go along these 2 paths. Okay. So here I've drawn all 6 possible Hamilton paths, right? Now, we can enumerate these paths by just writing down the sequence of vertices that we visit. If we do that, get ABC, ACB, CAB, BA or BCA, CAB. Uh-oh, I screwed this up. Thank you for correcting me. You guys were all thinking it. BAC. This is CAB. And this is a CBA. So here we see this correspondence. We see the 6 paths, we see 6 permutations of 3 letters, and we see the number 6 calculated by as a factorial. Okay. Now, why is it that why is it that 6 is the number? Why is it that it's 3 times 2 times 1? Well, okay, I've illustrated it out here, but let's say I had a complete graph of 4 or a 10 or whatever. So let's say I'm just looking at K, I don't know, 6. And I want to say that the number of paths, I don't want to draw 720 paths, right? But I want to say that the number of, let's say, permutations is 720, which equals 6 factorial. So why is that the case? Anyone give me any insight into why it might be the case that I get that number? This has to do with something we'll hit again later on. So I figured we'd do it now since we're seeing these numbers now. And we'll probably repeat it and remind ourselves later. So let's think of this. Okay, so we have letters A, B, C, D, E, and F. These are the letters that we put on our vertices, right? And we want to think of all different ways that we can write this in a sequence, or write a word with these letters used each once. It doesn't have to be a sensible word, just we'll call it a word. So that means I need 6 letters. It's like a little hangman thing we got here. Okay. And there is this notion, this multiplication principle notion, which tells us that we can sort of multiply, if we look in sequence, how many options we have, we can multiply our choices and we'll get the total number of possibilities at the end of the day. So if we're looking at the first letter, how many options do we have? If we haven't filled in any of the other letters, how many options do we have for the first letter? 6. We've got 6 letters. So first choice we have to make, we have 6 possible choices. But now let's say we've made that choice. We put something in here. How many letters do we have for the second letter? Okay, we cannot. So that's a good point, very good point. And I want everyone to hear that point, including those online. A permutation, you don't repeat. Can't repeat the same symbol. Permutation is you're reorganizing all of those, but you're only using each once. That's a permutation. So given that, we have 5 options here. So there are 5 options here. So we use one more letter. We'll have 5. And we fill that in. How many options do we have next? 4, right? We've used 2. We have 3 here, 2 here. And then once we're at the final stage, we've used all letters except 1. So we only have 1. We don't really have a choice. We just have 1 possible thing we can put there. This multiplication principle then says the total number of possibilities is take the product of each of these numbers. And that will give you the total number of possibilities, which is 6 factorial. Good. Okay. So that's how the game is played here. And that gives you the total number of possible paths. Now, what about Hamiltonian cycles? So the number of Hamiltonian cycles on Kn, anyone guess? Hmm?
K6, how many cycles?
On Kn. Okay, so let's say n equaling 3. Let's try 3. So let's say K3. We'll start with that. 6 for cycles. Yeah. So, okay, let me make an amendment here, because what we saw here, I remember last class, people said there are 3 paths. And I said there's actually 6. And that people said, well, you're ridiculous, Dr. Kerr, which I said yes. And they said, because these 2 paths are sort of the same, right? They look kind of the same. I said, no, they're not. The direction matters. So I still want to say the direction matters, even if you went to cycles. The direction does matter, even for cycles. However, if I complete something to a cycle, let me take this, for example, and complete it to a cycle. Here. Well, you can see there's only sort of one way I can do that here. But now I want to say that, in fact, this cycle does not, while the direction matters, a starting point doesn't. So my cycles are not, I don't care about whether I start here or start here. I got a cycle or a circuit. I don't want to think of starting anywhere for my circuit. So in other words, I got to this by adding an edge to this. However, I could have also gotten to that by adding an edge to this. In other words, adding this edge. It would have been the same cycle. Are people understanding what I'm saying? Does it make sense? No? Okay, it doesn't make sense. All I'm saying is that a cycle doesn't have a starting point, doesn't have an official starting. A cycle I want to think of as just sort of a loop in the graph. Not a loop, but a circuit. Yes. So in this particular case, for K3, there are only 2, right? There's this one, and then there's the one going in the opposite direction. So I'll just. So if we go here, then the opposite. Okay, good.
Would it be the same on, say, a square, 4 sides, because it's still only given.
For a square, yes. For a square, there'll also be 2 cycles. However, if we go to K4, we're not a square anymore. Right? A K4 is one of these guys. I'll draw it this way. I can go A, B, C, say D. Let me make this a little, sorry guys, let me make this a bit here. All right, so we have this guy here. Now, if we were considering cycles here, well, we have 4 factorial, which is 24 paths, and we can close them up. And we'll get a cycle for each one. So let's see here. Take several drawings here and see if we can. What's going on. So let's say we have a cycle like or a path A, B, C, D, coming from a single permutation. There's only one way to close that up to make a cycle, right? And that's just to add this extra path. right? However, we have another path, a Hamilton path, that would be like C, D, A, B, right? And we could have closed that one up and gotten the same cycle. So how many, let me ask you this, with this particular cycle, how many paths could I have closed up and gotten that particular cycle? How many Hamilton paths could I have closed up by connecting? I'm just thinking of the number. So, okay, there are 24 Hamilton paths. So of those, how many, if I took the last point in the path and connected it to the first point to make a cycle, how many of them would give me this particular cycle? Let's see. So I said if I took A, B, C, D, I close that up, I get this. However, and that means that I'm just going to add an A at the end. I'm going to go back to A. However, if I have B, C, D, A, and I close up at B, don't I get the same thing? Or if I have C, D, A, B, and close up at C, don't I get the same cycle? Any more? D, A, B, C. So I have actually 4 of those paths close up to give me exactly the same cycle. 4 of them do. Okay. So let's say I did something else. Let's say I started at A and I wanted to close up, I don't know, A, C, B, D. And I close up this path. Let's see. AC, CB, D. Okay. So that means I add this A here. So how many paths will I close up to get that particular cycle? Guesses? 3? 3 more, you mean?
4, because it's 4 times 6 and you have 24 total.
Okay, so there are 3 more. We can take it a little slower than that. There are 3 more, right? So for each, what I'm trying to say is for each of these cycles, there are 4 paths, Hamilton paths that I can close up to get them. And then as you're saying, we had 24 altogether. So 24 divided by 4 is 6. And so I'm not going to draw the other 6 of them because I will just be wasting everybody's time. So let me get rid of that. I got too ambitious there. But there's 4 more of them, 4 more cycles. But what I want to say is, well, let's take a look at that arithmetic a little bit. So the number of paths, Hamilton paths, in this case was 4 factorial, which is 4 times 3 times 2 times 1. And the number of cycles or circuits, sorry. Well, we grouped them, each of these paths into 4, we grouped each of these paths together into groups of 4. And so we divided this whole number of paths by 4. So it's 4 factorial divided by 4. Let's just write it out. 4 times 3 times 2 times 1 divided by 4. You guys know how to cancel, right? For fractions. So what is this called? Yes, it's called 6, but what else is it called? When I write it that way. 3 factorial. 3 factorial. The reason we want to write it that way is because guess what? You can do this when you're not 4, but when you're n. In other words, this procedure works for, K5, K6, K7, and gives us an answer, n minus 1 factorial. So this number here, minus 1 factorial. Good?
Sigh.
Yeah, Friday mornings. Yeah.
Okay, so just to clarify,
Uh-huh.
the n-1 factorial goes up with those two triangles, like that's like the final answer, like on a homework assignment or quiz, or something like that answer would be n-1 factorial.
Well, no, I mean, if I ask you a particular number, n, in this case, this number n is 3. So if I gave a particular number,
Oh, so then it's.
and then you get 3 minus 1, which is 2.
So then your answer is 2 factorial.
Yeah, it's 2 factorial. Well, you can write it as 2, but I love seeing something like this. Like if I see this, then I'm like, not only do you know that it's 2,
But-
you know where it comes from. You know, like this is the formula. Yeah,
Oh, sorry.
that's it.
Okay, makes sense. Thank you.
All right, guys. So factorials, as I was saying earlier, we can use them to answer all kinds of questions. Depends on the context. Here's another one. Another question about, I think we'll get into this cup stacking business. Okay. There's something called binomial coefficients. How many people have heard of this? People have heard of this? That's great. There you go. That's you've got both words. And then, has anyone seen this notation? There's also, I think computer scientists sometimes use this notation. I don't know really. There's other notation.
Are we your favorite class?
Huh?
Are we your favorite class?
This has been, it's been really pleasurable so far. You're fantastic.
Sorry.
You also teach like Calc 3 or something like way higher level than this.
I don't want to say
You're
anything.
done class.
Yes, I know. Calc 3 is the lowest level course I've ever taught.
Oh, awesome.
So we're in the dumb class. Just
No,
saying.
no, actually, that's not true. I taught a class for, you guys see, that's the thing. I had a friend who said, so you're teaching a class. And I said, that's not, my wife, she teaches, she doesn't do it now, but she used to teach English in Chicago high schools. Like, she's really brilliant, but she's has no love for math. So like, I appreciate you guys as intellectual giants, regardless of your mathematical background. However, I love math, so I'm going to share with you what I understand and what I like. So sorry if it's torture. Okay, binomial coefficients. Okay, these answer a lot of these questions, a lot of counting questions that you might encounter. And there's a formula for them. And I'm going to write the formula, which is going to look like ridiculous, but it's a formula. I know you've seen something like this. Well, I don't know if you've seen this. Have you seen this? Who's seen this? Yeah, you've seen it. Now it looks familiar. If you haven't seen factorial, it will be like, what? I don't remember. But this is like a bad dream in high school or middle school. Why do you learn trig? That's my question, is why is trig a class? I never understood that. Not to like rant about, I mean, I know I rant, but like, it is ridiculous to have trig as a class. That's the worst thing that exists in my opinion.
Sometimes you capitalize your N, sometimes you don't. Is it all the same thing?
Okay, that's a good question. So I'm following the book's notation with capital N for case of N. And I think although I've seen it with that lowercase n. Normally I don't capitalize my N's for natural numbers, but if you're confused, ask and I'll clarify. Okay, this is a formula. It's not the most practical way of finding these numbers, at least for small n and a small k. There's another way. Anyone know another way of finding these numbers? Anyone remember a vague memory? Okay. All right. So now I know you've all seen this. I'm going to start writing it down, and you're going to be like, "Oh, yeah, I've seen this." So let me give n equal. I'm going to put a table. I'll set n equals 0, 1, 2, 3. I think this will be enough. Okay. And I'm going to do, okay. So for this to work, k has to be between 0 and n. So you can't have k being larger than n or smaller or being negative. So when n is 0, there's only one possibility here, k has to be 0. So you have 0, choose 0. That's actually, if you remember the convention, 0 factorial is 1. This is just 1 over 1. So you get 1 here. Now when n is 1, you have two possibilities. So you can have k being 0 or 1. Right here, you could have k being only 0. When k is 0, you get 1. When k is 1, you also get 1. Okay, so now let's say n is 2, then all the integers between 0 and 2 are 0, 1, and 2. Actually, whenever k is 0, you'll get 1. And whenever k is equal to n, you get n over n factorial over n factorial times 0 factorial. That's always going to be 1. And yeah. However, here, when you get 2, let's just calculate 2, 1, it's going to be 2 factorial, which is 2 over 1 factorial, which is 1 over times 1 factorial. That's 2. Just compute. Okay, triangle. People remember now? Yeah, is it a bad memory or a good memory? It's a vague memory. It's like a forgettable dream. It's like I didn't really care about it then. I don't care about it now. Huh? Yeah, I'll bet you did, right? They worship this stuff. They worship this. Look at this. You guys remember who knows what I'm drawing here? Raise hands. Who's seen this before? Okay, 2. All right. There for 0, here you have 1, 2, 3. I need to keep going. Okay, I'm just going to put the numbers in. When k is 1, you'll get a 3. When k is 2, you'll also get a 3. Here you have one more, 0, 1, 2, 3, 4. Again, at the extremes, you always get 1. Actually, right next to the extremes, you get n. And now here you get a surprise. 4 choose 2. 4 factorial over 2 factorial times 2 factorial. Right? 4 minus 2 is 2. So that's 4 factorial over 4, which is, we've seen, 24 over 4, 6. Has anyone seen this before? How many people have seen it now who hadn't seen it before? You guys have really never seen this before? Guys are, gotta send me the name of your teachers. Send them some hate. The worst. So look at this. There's a rule. Yeah, you've seen it? The 6 is this computation. So I'm going 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. This will be 6.
So all of that equals 4 over 2 equals 4, whatever.
Yeah, this whole thing is 4 factorial, which is 24 over 2 times 2. Yeah. Do you guys notice how you can, if you don't want to use this horrible formula that I've introduced you guys to, which is a lovely formula, you don't want to, you don't have to if you're doing this beautiful, wonderful triangle, right? You don't have to do it. There's another way. Who remembers this triangle? What's the other way?
There's the big triangle visual.
Oh, no, okay, we'll get to that in a second. We'll get to the, you're ahead. Keep on, yeah, you keep on getting ahead of me too.
That always happens to me.
Just
sorry.
Yeah.
like this class.
Okay,
Oh,
slow
no.
down, lady.
Don't give me a tennis. I'll fit.
All right. Anyone? 1 + 1 = 2. 1 + 2 also equals 3. 3 + 3 = 6. If I add 2 consecutive, I'll get what's below it. Any 2. Of course, if I want, here I'm going to kind of give myself ones going on forever, just so I don't have to worry about that. So what do you think? What do you think this guy is going to be? Sorry. 10. That's correct. It is going to be 10. The next one will also be 10. 5, 1. We can keep going. Now you guys don't have to do factorials, right? It's pretty good stuff, right? 6, 15, 20. Very good, guys. You guys are already mathematicians.
I get my PhD in mathematics.
Well, and it may take a little more. Even here at K-State, it may take No, you will not forget this stuff. This will not, I'm going to send you guys emails for the next 10 years. You're going to be like, oh, it's that professor.
Block.
Get blocked. Take legal action. This guy keeps emailing me the Pascal's triangle.
Oh, that's what it's called.
Pascal's triangle. You guys remember Pascal? Nope.
I don't remember him, but I feel like I've heard the name before.
Pascal's triangle.
Isn't that the lizard and angle? Or the gecko?
I'm sure there's all sorts of guys, there's all sorts of popular culture where they like name things after legit math
That was my
because
dog-
math is legit.
that was my math teacher's dog's name.
Yeah,
That makes
right.
so much sense now.
So Pascal was like, I think like 1600s. Of course, he was like a clergy because only people that could do math back then were who had enough time were like religious people or something. Anyway, he did a lot of mathematics, a lot of good mathematics. But then at some point he gave mathematics up and said it was the devil's work. But he still loved it. He loved math, right? He had like this bad relationship with math where he really was in love with it, but it was the devil. And so every time he like thought about math, he would like you know what I'm talking about? Like he had like he would put the iron belt on and like hit himself with it to like get rid of the devil thoughts, the math devil thoughts.
Was he Catholic? That sounds like something Catholic.
I'm telling you guys, he was crazy. So crazy time, but I don't know if you want to think it's the devil's work, it is what it is, but it's some good stuff. This is some,
So that makes you say it.
I've been called worse.
In other words.
No, I try not to take a position on anything. This is a very, very useful triangle. These numbers are very, very useful. So here, just to be clear, the rows in this triangle, these rows are, well, here, let me, before I mess it up, let me copy. Okay. The rows in this triangle are given by this number n, okay? So this is n equaling 0, n equaling 1, n equaling 2, and so on, right? And these sort of, not quite columns, but sort of the sides are given by k. So if we look at this side, oops, this is k equaling 0. This whole bit is k equaling 1. This whole bit is k. And so, okay. So the entry then if you look at the nth row and the appropriate k is n choose k. So the logic. Now, Pascal's triangle has some cool things. If you like to color, I guess you guys are a little old for that, but then you have a future. Elementary school. So what you can do is let's color the odds blue. Color the odds blue and color the evens red or something. You'll never guess what you get. Odds, all the odd numbers. No, it does not make sense. Okay. Right? I don't know. What did I say? Red? Look at this guy. That's the triangle. Good point.
Oh my God.
If you go and do this for a huge Pascal triangle, yeah, you will get something that looks like that. Scaling out. Yeah, it's weird. Very weird. If you do it and you divide by like 3, for example, and now you have 3 colors and you look at the remainders, you can have 0, 1, or 2 when you divide by 3, and you use the colors for remainder 0, remainder 2, and remainder 3, you get another slightly different looking, but really pretty picture as well. You can keep on going. Very strange patterns. Why am I talking to you guys about Pascal's triangle? Well, as I said, we are going to be talking about this later in the class, so might as well talk about it now, because these numbers, they count things. And they count something that we are already interested in. So if we look at n choose, say, 2, this counts the number edges on k. Now I'm going to use the lowercase n. An idea is, think of the way the language here. This is called n choose 2. And what it means is if you have n symbols, it's counting how many ways you can choose 2 of those symbols. But if you think of the complete graph on n symbols, between any 2 symbols, there's an edge. So the number of ways you can choose 2 symbols is exactly the number of edges in complete graphs. And let's just double check to make sure. So we're looking very much at this column. That's the 2 case. So if we look at our graphs, that's K2. Here's K3. Here's K4. I guess I've drawn it the other way. K4, and then K5. You can draw this one. So if we look at K2, there's only one edge. Right. K3, 1, 2, 3, we have 3 edges. K4, you can count 1, 2, 3, 4, 5, 6. And then K5, if you count, you can see that there's 5 on the perimeter, and then there's 5 in the star. You get 10 edges. So these numbers will accomplish counts like this. These are also, these for k equaling 2, they're also called triangle numbers because of, they also count the number of dots in a triangle. So if you have one triangle, that's height 1, that. Here's a triangle with 3. You can do this. In fact, this is a story too, which I have just enough time for. So you can look at the number of triangles. You can see this is 1 plus 2, this is 1 plus 2 plus 3. So let me tell this quick story and then we'll go for the weekend. We're gonna have to do a little more graphs on Monday. So there, have you guys heard of Gauss? You guys know Gauss? Uber Gauss? Like the best mathematician ever lived, ever? Maybe, by some people. When he was in elementary school, he was punished by his teacher and sent in a corner. And the teacher said, add all the numbers between 1 and 100. And he came back with the answer, which you guys will come up with very quickly, because he understood this relationship, kind of had figured it out himself, that you could count up all the numbers and use instead just 100. This is a very smart guy. Smart kid. All right, guys. See you Monday.
See you Monday. Thank you.
Is it possible to print out the homework assignments? Because I'm at the university still has to order the book is ordered, but is it possible for you to print out the homework?
Print like the copy from the book and include it.
Yeah, because the university had to order the book until like Wednesday. I don't want to get too far behind.
Yeah, I can. I
Or
don't
you know what?
Do I have it? I might have brought. I don't know if I brought it in today. But I'd have to. Yeah, I guess I could take a picture and post it. I don't know. I'm sure I'm breaking some laws. I don't care though. Like, let me just do it for the first couple of chapters.
Yeah, awesome. Just like the questions. Just I don't want to get too far behind on the homework.
Yeah, I understand.
All right, thank you so much. Appreciate it.
I have a question. So
Let me just stop the meeting.